In this short video, I'm going to talk about the difference between dynamic and static data placement, why this is critical in scaling your storage system, and why, with the rise of object storage, this has become more and more relevant. But first, let's step back and see how we got here in the first place. Back at the turn of the century, people were deploying big monolithic file systems. They would deploy big Sun, IBM, HP servers and present to their organization a very large multi-terabyte file system, which was very big at the time. Well, the file systems got too big, the inode table started falling apart, consistency checks started taking too long, so we just needed to come up with a better way to manage a large amount of data in a file system. So we started looking at distributed file systems. The idea of spreading your files over multiple file systems and then presenting them as a single file system. And this was done by adding a software layer that managed the multiple file systems and did the abstraction to make it appear as if you were working with a single file system. But there wasn't a well-defined set of instructions that described how we could distribute these files over the file system and then get them back when we needed them back. So in 2001, some smart people at MIT came up with something called the CORD protocol. And one of the things the CORD protocol did was define an algorithm how you could evenly distribute data across these multiple file systems and how to get it back when you wanted it back. Essentially, it works like this. Sally wants to store a spreadsheet in this file system. So Sally hands her file off to software, which takes the file name, runs that file name through a hash function, and produces a hash of that file name. That hash is like an address. It says which node to store that file on. One of the characteristics of this architecture is how the nodes talk to each other. Any single node was not aware of all the nodes in the cluster. It was aware only of its adjacent nodes. So it started looking like a ring, and as it evolved, it became known as the ring architecture. Let's define this. A ring is made up of a cluster of nodes. A ring is divided into partitions. Each node is assigned one or more partitions. In this example, each node has one partition, and for the duration of this video, each node will be responsible for a single partition. Each partition is assigned a hash range. And finally, a ring is closed when there are no gaps in the hash ranges. Let's take a closer look at how this works. Sally wants to store her spreadsheet. So she hands the spreadsheet off to software. The file name goes through the hash function. In this case, 3741 is the hash value, and 3741 falls in the range for the partition being managed for node 2. So Sally's spreadsheet is stored on node 2. So, in review, the ring architecture is based on MIT's CORD protocol. It was designed for a distributed file system, and file storage location is calculated based on the file name. So let's see how this works in modern scale-out storage systems. Remember Sally's spreadsheet? It's sitting over there on node 2, and over time, you're going to fill up your storage system. You're either going to run out of capacity or you're going to run out of compute resources. So we need to scale out. We want to add a node 6 in this case. But remember this rule, each node is assigned one or more partitions. But there is no partition for node 6, so what we have to do is repartition the ring so we can add a partition. And now, node 6 can be responsible for the new partition. But what about this rule? Each partition is assigned a hash range. Well, there is no available hash range for node 6. So what do we have to do? We reassign the hash ranges for the existing partitions. So on node 1, we will change the hash range to 0 to 1667, and we'll go around the ring, and we'll give everyone a new hash range, and now we have some free space so we can assign a hash range to node 6. But what does that do? Remember Sally's spreadsheet sitting on node 2. So now that we've scaled out, when Sally wants to get her spreadsheet back, the name is run through the hash function 3741, but now 3741 is pointing to the partition being managed by node 3. So Sally's spreadsheet is on the wrong node. Now Sally will get her spreadsheet back. There'll be exception processing that can deal with this, but the point is, because of the rebalance, we have files on the wrong nodes. So how do we fix that? Well, we do have a mechanism to fix that, and it's called a rebalance. A rebalance is when we relocate files from the partition they are in to the partition they should be in. And this is not renaming files, this is the actual movement of data across partitions, across systems, and across regions. So after the rebalance, Sally comes in to get her spreadsheet, the name is run through the hash function, and now 3741 is pointing to the correct partition that contains Sally's spreadsheet, so the ring is once again complete. Quick review. When a ring is scaled out, it must be rebalanced. And rebalance is the physical movement of files across devices, networks, or regions. And something to note is that the time it takes to rebalance does not scale linearly. As you increase the number of devices and the number of files that need to be rebalanced, you increase the amount of exception processing that takes place, which causes that nonlinear scale. Let's see what happens to ring during a hardware failure. In this case, we lost node 3. Here comes Sally to get her spreadsheet back. The file name goes through the hash function 3741, but 3741 is pointing to node 3, and node 3 doesn't exist. Okay, again, Sally will get her spreadsheet back. Different storage systems have different mechanisms to deal with this. Mirrored copies, multiple copies, whatever. But the point is, exception processing has to take place to get Sally her spreadsheet back. So what happens now? Remember the rule that a ring is closed when there are no gaps in the hash range, and we have a huge gap in the hash range. Node 3 is completely gone, so what do we have to do? We have to reassign hash ranges to the remaining partitions, which in turn causes a rebalance. So the impact of a hardware failure with the ring architecture is the hardware failure will break the ring, and a rebalance is inevitable. And hardware failures are an urgent matter that need to be dealt with immediately to avoid multiple rebalances. So let's take a look at ring and how it works in an object storage system. Underneath the covers of an object storage system is a distributed file system. So many vendors have adapted the ring architecture for their underlying distributed file system. So let's see what happens. When Sally wants to put her spreadsheet in this storage system, it doesn't go in as a single file. It needs to be erasure encoded. So the file goes through an erasure encoding algorithm, and in this case, it produced 15 parts. Now the number of parts can vary depending on the durability of your object storage system. In a very durable system like ActiveScale, you can get up to 20 parts. So what we do is take each one of these files, run its name through the hash algorithm to determine placement in the distributed file system. The net effect of erasure encoding is that the underlying distributed file system can have 15 or 20 times more files than your traditional file system. So what does this mean? Erasure encoding greatly amplifies the number of files in the underlying distributed file system. And as the number of files, disks, and the compute resources increase, there are more things that can fail, therefore more rebalance triggers. And a ring will fail when the time to rebalance exceeds the time between rebalance triggers. So let's take a look at a more modern approach to data placement. Let's look at ActiveScale's dynamic data placement. DDP was designed specifically for object storage and the extreme numbers of files and objects that go along with that. With DDP, each disk is considered an independent storage unit or block store. And these block stores have attributes. And data placement is determined based on storage policy and by evaluating the block store attributes to determine the most ideal location for a file. Let's take a look at some of these block store attributes. Well, a block store has an ID. A block store has a location. We know which rack the block store is in. We know the storage enclosure. We know the sled, and we know the slot that block store is in. But there's additional attributes. We know the capacity of that block store. And we know how much of that capacity is available. This is important because you want your block stores filling up at a relatively uniform rate. We know if the block store is online. A block store can be offline for many reasons. It doesn't necessarily mean a failure, but to write to the block store, we need it to be online. And we know the demand on that block store. In this case, the block store has a demand of 13%. That means the block store is participating in I/O 13% of the time. So with DDP, every block store is an independent storage unit. And every block store has a set of attributes. And DDP uses those block store attributes to determine the most ideal location for data. Let's take a closer look. In this case, we have a distributed object storage system across 3 data centers. And Sally wants to put her spreadsheet in there. Well, the first thing we have to do is erase or encode that file. And like the previous example, we get 15 parts. Well, how do we place those parts? Let's just take a look at one of the parts and see how it works. Storage policy will tell us the data center. It also tells us the preferred rack and the preferred enclosure. But inside that enclosure, we have several block stores. In this case, 25 block stores. And this part can be stored on any one of them. But how do we determine the most ideal location? Well, with the 25 block stores, let's consider that our selection set. So we evaluate the block store attributes. We need the block store to be online, and in this case, there's one block store that is not online, so it's eliminated from the selection set. And we look at block store availability. Not only do we keep track of the capacity of block stores, we keep track of how much of that capacity is available. In this case, we set a threshold of 70%. We're looking for block stores with 70% available capacity, but that threshold is a variable. If we can't find any block stores that meet that threshold, we can assign it a new threshold. And now we can look for block stores with 50% available capacity. So any block stores with less than 50% available capacity are filtered out of this selection set. And now we look at block store demand. This is an indication of how busy the block store is. To avoid I/O hotspots, block stores with lower I/O demands are preferred over block stores with higher I/O demands. So we set a threshold, in this case 20%. We find a few block stores that are pretty busy, so they're filtered out of the selection set. And so now, any one of the remaining drives that's still in the selection set is a valid storage location for this part. So we can just randomly select a block store from the selection set, in this case the block store with the ID HDD12. So in review, DDP is a weighted variable selection algorithm, and the algorithm accommodates failed or offline hardware. Block stores with higher available capacity are preferred to ensure an even data distribution. And block stores with lower I/O demands are preferred to prevent I/O hotspots. So let's take a look at DDP and how it's affected by scale out. We'll use the same part as in the previous example that was going into Data Center 1, Rack 2, and Storage Enclosure 5. But now we've added more block stores, we've scaled out. So what happens? We go through the same process. Block stores that are not online are filtered out of the selection set. Block stores that don't meet the availability threshold are filtered out of the selection set. And block stores that don't meet the demand threshold are filtered out. So we can now choose any of the remaining block stores in the selection set as a storage location. So let's contrast DDP with Ring. Ring, which is a static data placement algorithm, assigns storage locations by hashing a file name. DDP uses block store attributes to determine the most ideal location for a file. Ring assumes the partitions are static, and it requires exception handling to deal with changes in the ring. Where DDP assumes the object store is always changing, and changes in the cluster have no effect on data placement. And with hardware failure, a hardware failure breaks the ring, and replacing hardware becomes an urgent matter to minimize the impact of the rebalance. Where with DDP, failed hardware has no effect on data placement. DDP is a fail-in-place system. Hardware can be replaced during a convenient maintenance window. With scale out, Ring must be repartitioned and rebalanced. And the physical movement of petabytes of data as a background process can take months. With DDP, scaling out is simply adding additional resources, and it has no impact on existing data. For more information on ActiveScale and DDP, visit our website.